Welcome to a lecture on motion and gravity. In this lecture, we'll be focusing on Newton's laws of motion. The ancient astronomers did not make connections between gravity and the motions of the celestial bodies. Newton, however, did make these connections, and he made these connections using math. He developed calculus, and he developed his laws of motion, including inertia. He was able to do this primarily based off of the work of Galileo. Inertia is the tendency for an object to stay at rest if it's resting, or for it to stay in motion if it is in motion. Galileo saw that the ball rolling down an incline would speed up and a ball rolling up an incline would slow down. He hypothesized that in the absence of friction, a ball rolled on level surface would move at a constant speed. Under normal circumstances here on Earth, we have friction, and that would cause a ball to slow down. Galileo's observations brought Newton to his first law of motion, which is also called the law of inertia. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. So again, the object is going to resist the change. This diagram shows you Newton's first law of motion, inertia. Each ball represents the ball's position at every second interval of time. This diagram also does not take into consideration friction. Friction would normally slow a ball down. If the ball is moving on a flat surface, the speed is going to be constant. As it starts to move downhill, you'll see that the ball starts spreading apart, indicating that it's moving faster. If that ball is then going to move uphill, you'll see that the distance between the balls is getting shorter because it is slowing down. And if the ball is moving on a flat surface, you'll notice that the distance between each of the balls is evenly spread apart, representing a constant speed. A force is something that acts on an object in terms of either push or pull. For a body to overcome inertia, an unbalanced force must act upon it. So if it's resting still, an unbalanced force, if you kick a ball, that would be the unbalanced force, and it will overcome inertia. It'll overcome its resting state. In a tug of war between two exactly equally matched teams, the rope does not move because the forces are balanced. When forces are balanced, the net force is zero. If two teams are not equally matched, the net force on the ropes was unbalanced, and therefore the rope will move. Force is measured in a unit called newtons. A newton is the force required to give a mass of 1 kilogram an acceleration of 1 meter per second. In this example, if I have the person on the left giving a force of 2 newtons and a person on the right pushing at a force of 2 newtons, my net force would be 0. Therefore, the box would not move. An unbalanced force acting on an object causes the object to undergo what's called acceleration. Acceleration is a change in the object's speed, or it could be a change in the object's moving direction, or it could be both. A common misconception is that acceleration means going faster. But remember, it's just a change. That can mean going faster, going slower, or it could just simply mean a car is going the same speed and maybe going around a sharp curve and changing direction. Uniform motion is when an object moves at the same speed and the same direction. Since nothing is changing, it is considered uniform. Acceleration is a change in speed or direction. In the case of this diagram, we're just looking at speed. So the car started out at 0, and then it's at 20, then it's at 40, then it's at 60 miles per hour. So it is speeding up. This diagram also shows acceleration. The car may be traveling at the same speed, but the direction's different. So this is the old velocity, here's the new velocity. They changed speeds. Imagine you're rolling a ball attached to a string above your head. The tension in the string is a centripetal force. This is a force that is going to pull the ball towards the center. If you let go of the string, however, the ball will travel in a straight line. It will not continue in a curved path. The reason why it will not continue a curved path is because the string is no longer pulling on the ball towards the center of the circle. So in this diagram, the ball will continue around that circular path because the string is pulling it towards your arm or your hand. In the picture B, the ball would be moving in a circle. The string would be pulling the ball towards your hand. However, if you let go of the string, the ball will continue in a straight path wherever it lets go. With no unbalanced force acting on it, the ball continues moving at a constant speed in a straight line. However, here on Earth, we do have an unbalanced force. This is called gravity. When you let go of the string, the ball will travel at a constant speed straight in a horizontal fashion. As the ball is traveling horizontally, the ball will also be falling vertically under acceleration until it hits the ground. The path through space followed by the ball is a combination of this horizontal and vertical motion. This example does not take into consideration air resistance. So if I were to throw a ball, it would be moving horizontally at a constant rate. Vertically, it would be increasing its acceleration due to gravity. So if we put the two together, you would get a curved line. Here's a thought that Newton had. Suppose you have a cannon at the top of a high mountain. If you put a small amount of gunpowder, the cannonball will move slowly and then hit the ground. If you put a large amount of gunpowder, it'll travel faster, but it will still fall down. However, it would go a greater distance. Each increase in the gunpowder, the cannonball will move faster, therefore travel farther before hitting the ground. In each case, the cannonball hits the ground because of the gravitational force acting on it, pulling it towards the center of the Earth. With a big enough powder charge, the cannonball gains enough speed so that it will never hit the ground. At this point, the cannonball would be considered to be in orbit. The cannonball in orbit never hits the ground because the Earth's surface curves away from it. This experiment also ignores the fact that we do have air resistance on Earth. Air resistance would slow down the cannonball. We can use the example of the cannonball to explain how the moon orbits the Earth. The orbital speed is high enough that the moon never strikes the Earth. There's a balance between inertia and the force of gravity. This is what maintains the orbit. Motion is defined by a change in a position of an object. Remember, we could be talking about direction or speed. So if the direction and speed are both constant, we call that uniform motion. Velocity is another term we'll be using. Velocity refers to speed and direction of an object. If I say a car is moving at 50 miles per hour, that's describing the speed. If I say a car is moving 50 miles per hour to the east, that's describing velocity. A change in speed or direction is an acceleration. The term mass can describe an object's measure of inertia. Remember, inertia is the resistance to change. Mass can also mean the amount of matter in an object. On Earth's surface, the gravitational force acting on an object is the weight of an object. By definition, your mass will not change. If you're 75 kilograms here on Earth, you'll be 75 kilograms here anywhere in the universe, like, say, the moon. However, your weight will change because a weight is a measure of the gravitational force. So if you go to the moon has less gravity than the Earth, therefore you'll weigh less on the moon. When applying this to inertia, the more mass an object has, the more it resists the change. Imagine trying to move a train. A train has a lot of mass, it's going to resist you pushing on it. It's not going to move very much. Newton's second law states that the amount of acceleration that a force can produce depends on the mass of an object being accelerated. The equation would be F equals ma. Force equals mass times acceleration. In these two examples, we have an empty cart with a low mass and a full cart with a high mass. Both carts are given an equal force. The cart with the low mass has a higher acceleration and can travel farther. The full cart will have a small acceleration and not move very far. Newton's law of universal gravitation states that every mass exerts a force of attraction on every other mass. The strength of the force is directly proportional to the product of the masses divided by their square of their distance of separation. So in other words, the more mass an object has, the more gravity it's going to exert. The closer two objects are, the more gravity they're going to exert in between each other. This diagram shows the components of the equation. The two different masses could also be written as m1 and m2. You may see that in some equations. The radius, so the distance, goes all the way to the center of the mass. Not to the edge of the mass, but the center of the mass. Since mass 2 has a greater mass, it's going to exert more gravity. So again, M1 and M2 are the two different bodies. R is the radius between them, or the separation. G is the gravity. Let's take a look at the units. Force is measured in mass times kilograms over second squared. If we plug that into the formula, we have G for gravity. Mass of the object 1 times mass of object 2 would give you kilograms squared. Kilograms times kilograms give you kilograms squared. And we divide that by radius squared, so meter squared. Now if we rearrange this to get G by itself, if I multiply both sides by meter squared, I end up with the meters cubed on this side. If I divide everything by kilograms squared, this kilogram gets canceled out and we're left with 1 down below. Now if we rewrite this equation, G would be meters cubed over kilograms times second squared. Those would be the units for G. From the equation we can see that the greater the masses are, the greater the gravitational force is. We can also see that the greater the separation between the two masses, the weaker the gravitational force is. Say you step on a bathroom scale and it reads 160 pounds. Your location on the Earth's surface is about 4,000 miles from the planet's center. Now if you imagine you step on that same scale that is 4,000 miles above the Earth's surface, in essence you're doubling the distance from the center of the Earth, what would your new weight be? Your new weight would be 40 pounds. Your distance from the Earth's center would be now 8,000 miles instead of the 4,000 miles. This is double. So in the equation you would take r squared. Well, if r was equal to 1 and you doubled that, r would now be 2 squared. That would equal 4. Since it's in the denominator, that is 1/4. Gravity acts as if it's concentrated in the center of the Earth or some body. When you move away from the Earth's center, the force of gravity acting on you is inversely proportional to the square of the separation between you and the Earth's center. Your weight would be slightly less on the top of Mount Everest than it would be here in Lidditz. Granted, it's only a fraction of an ounce, but when we talk about astronomical distances, then this will become more of a factor. Your weight will be slightly more in Death Valley, which is below sea level, than it would be in Lidditz because you're closer to the center of the Earth. The law of gravity is an example of a inverse square law. When two objects interact with each other, they create an equal and opposite forces on each other. This is known as the law of action-reaction. Take this for an example. If you're standing on a frozen pond with a little bit of water on top, this will reduce the friction to almost zero. Say you have a snowball and you throw it away from you. You will exert a force on the snowball, and the snowball will exert a force on you. You will move in one direction, and the snowball will move in an opposite direction. Now, since you have more mass, you have more inertia, you're not going to move nearly as far. Since the snowball has less mass, it will have a higher acceleration, and it will move farther. Here's another example. If you have two people on a skateboard, person A pushes person B, both people are going to be moving in opposite directions. Take the Earth-Sun system. The Sun has about a mass of 300,000 times the mass of the Earth. Therefore, the Earth is going to have a higher acceleration, 300,000 times greater than the Sun. Remember that circular motion is accelerated motion. The Sun is revolving around a point between the Sun and the Earth. It just so happens that that point is somewhere inside the Sun. This is similar to a majorette's baton. One end has more mass than the other end. Therefore, it's going to spin around the center of mass, which is not exactly the center of the object. Your weight is simply the gravitational force existing between the Earth and your body. Weight equals mass times gravity. The value of G depends on the Earth's mass and the Earth's radius. In order to shoot a rocket into outer space, the rocket must reach what's called the escape velocity. If the rocket's velocity is lower than the escape velocity, it will fall back to Earth. The escape velocity is found by using Newton's law of gravity and his laws of motion. You would take the square root of 2 times g, which is the universal gravity constant, times the mass divided by the radius. The Earth's escape velocity is 11 kilometers per second, or 25,000 miles per hour. Since the Moon has a much lower mass, its escape velocity is 2.4 kilometers per second.